Good evening, friends. We'll start API 571. Okay, and uniform or localized loss. Amine corrosion. General and localized corrosion that occurs principally on CES carbon steel in amine treating process. Corrosion is not caused by amine itself, but results from dissolved acid gases, CO2 and H2S. Amine degradation products, heat stable amine salts, HSAS, and other contaminants, primarily carbon steels. 300 series SS and highly resistant. Corrosion rates increase with increasing temperature, particularly in rich amine service. Temperatures above about 220 degrees Fahrenheit. 1 minute. (104°C) can result in acid gas flashing and severe localized corrosion if the pressure drop is high enough. Corrosion depends on design and operating practices, the type of amine concentration, contaminants, temperature, velocity, all this. H2S, CO2, mercaptans removal units, crude coker, FCC, S2A, reforming, hydroprocessing, and tail gas units, regeneration boilers, regenerators, lean rich exchangers, hot lean amine piping, hot rich amine piping, amine solution pumps, and reclaimers. So appearance, carbon steel and low alloy steel suffer general uniform thinning, localized corrosion, or localized under deposit attack. Thinning will be uniform in nature when the process stream velocity is low, while it will be localized for high velocities associated with turbulence. Visual UT scan or profile radiography, corrosion monitoring with corrosion coupons and or corrosion probes. Monitoring should target the hot areas of the unit such as the reboiler, feed and return line, the hot lean rich amine piping, and stripper overhead condenser piping. Proper operation of the amine system is the most effective way to control corrosion with particular attention and acid gas loading levels. Refer 5.2 amine stress corrosion cracking. The next one, ammonium bisulfide corrosion. Alkaline sour water. Aggressive corrosion occurring in hydroprocessing reactor effluent systems and in units handling alkaline sour water, localized corrosion. Carbon steel is less resistance plus 300 series SS duplex SS aluminum alloys and nickel alloys are more resistance depending on ammonium bisulfide NH4H2S. Sorry, NH4HS salts Precipitate in the reactor effluent streams when temperature drop to within the range of 120 degrees Fahrenheit to 150 degrees Fahrenheit. So 49 degrees centigrade to 66 degrees centigrade. Okay, NH4, HS concentration, velocity, and localized turbulence, pH temperature, alloy composition, and flow distribution are all critical factors to consider for 5.4. Hydroprocessing unit, FCC units, sour water strippers, SWS amine units, delayed cooker, aluminum exchanger tubes, AE are susceptible for erosion corrosion. Refer 5455. General loss in thickness, localized corrosion at bends when concentration above 2% by weight. Low velocities cause localized corrosion. HE tubes fouling, corroded admiralty brass and copper tubes. Corrodes. Sampling of NH4H2 to determine concentration of HE tubes inspection by ECT, UT, and profile RT of high and low velocity areas. Monitor water injection, flow meter. Careful design when NH4HS concentration increase 2% weight, above 8% weight, plus maintain velocity 10 to 20 fps. For carbon steel, use alloy 825 duplexes when velocity is above 20 fps. Water injection to dissolve NH4HS. For SWS socket welded, use titanium alloy C276. Erosion, corrosion. Ammonium chloride corrosion. General localized corrosion upon pitting, normally occurring under ammonium chloride or amine salt deposits when in the absence of free water phase. All common materials are susceptible in order to increasing resistance. Carbon steel, low alloy steel, 300 series SS alloys, 400 duplex, SS 800, 825, alloys 625, C276 and titanium. Above the water dew point 300 degrees Fahrenheit. 149 degrees centigrade. Corrosion rates increase with increasing temperature. Concentration in H3, HCl, H2O. For amine salts, temperature and water availability are the critical factors. Crude tire overheads, hydroprocessing, catalytic reforming, FCCU, and coker fractionation units. Salts have a whitish, greenish, or brownish appearance. Water washing and steam out will remove deposits, or the evidence to fouling may not be evident during the internal visual inspection. Corrosion underneath the salt is typically very localized and results in pitting. Corrosion rates can be extremely high. Localized corrosion difficult to locate RT or UT thickness or wall loss. Monitoring of feed streams, the intensifying dew point temperature, later temperature monitoring. Corrosion proofs coupons are useful. Limiting salts and chlorides through desalting and or adding caustic water wash to flush salt deposits. Filming amine inhibitors or neutralizers HCl corrosion. Hydrochloric acid corrosion damage in refineries is most often associated with dew point corrosion, in which vapors containing water and HCl condensate from overhead steam of a distillation fractionation of stripping tower. First water droplets or condensate can be highly acidic, low pH, and promote high corrosion rates. All common materials constructed in refineries, alloy 400 and nickel-based titanium resistance to dilute HCl. The severity of corrosion increases with increasing HCl concentration and increase in temperature. HCl acid concentration, temperature, and alloy composition refer pg. 510 HCl corrosion is found in several units, especially crude and vacuum units, hydroprocessing units, and catalytic reformer units. So carbon steel, low alloy steel suffer general uniform thinning, localized corrosion. Under deposit attack, 300 series SS and 400 series SS will often suffer pitting attack, and 300 series SS may experience chloride stress corrosion cracking. UT for general thinning, localized corrosion, pH corrosion monitoring, water sampling. Corrosion proofs or coupons refer PG 512, water washing, caustic injection, chloride control generally before 20 ppm in overhead, accumulator water, NH3 amine neutralization into water, minimize HCl in H2 streams, refer page 512, ammonium chloride corrosion, chloride SCC, and localized corrosion. High temperature H2S corrosion. The presence of hydrogen in H2S streams increase the severity of high temperature sulfide corrosion at temperature above 500 degrees Fahrenheit. or 260 degrees centigrade. This form is sufficient to usually result in a uniform loss in thickness associated with hot circuits in the hydroprocessing unit. In order to increasing resistance, carbon steel, low alloy steel 400 series SS and 300 series SS. Temperature above 500 degrees Fahrenheit and increase with increase in temperature and H2S concentration. The major factors affecting high temperature solidification are the temperature, the presence of H2, and the concentration of H2S and the alloy composition. In high temperature H2S stream, all hydroprocessing units such desulfurizers, hydrotreaters, and hydrocracking units downstream of hydrogen injection point, uniform metal loss on process side in formation of iron sulfide scale. Scale is 5 times the volume of metal loss and maybe multiple layers, tightly adherent grayscale. UTRT-VT for metal loss, actual temperature monitoring against design temperature, process simulation checks for H2S levels. The corrosion damage is minimized by using alloys with high chromium content, 300 series SS, such as types 304L, 316L, 321, 347 are highly resistant at service temperatures. High chromium content, high temperature solidification in the absence of hydrogen. Hydrofluoric acid HF acid corrosion. Corrosion by HF acid can result in high rates of general and localized corrosion and may be accompanied by hydrogen cracking, blistering, and HIC, SOHIC. Carbon steel, copper nickel alloys 400 low alloy steels, 300 SS and 400 SS are susceptible to corrosion and are cracking and are generally not suitable for HF service. Other nickel-based alloys such as alloy C276 used. Corrosion rates increase with increasing temperature and decreasing HF concentration, increasing water content above 150 degrees Fahrenheit. So HF acid concentration, water content, temperature, alloy composition, and the presence of contaminants including oxygen and sulfur compounds are controlling factors. Piping and equipment in the HF alkylation unit, flare piping and downstream units exposed to acid carryover, HE tube and bundles, heat exchanger tube and bundles, some bore piping, deadlocks, flange fishes, ISO strippers, and depropanizer towers. Localized general or severe thinning of carbon steel, cracking due to H2 stress cracking, blistering, HIC, SOHIC damage, significant fouling due to iron chloride scales, alloy 400 shows uniform loss in the thickness but not significant scaling. Non-SR alloy 400 is susceptible to SCC. When contact with moist HF vapor in the presence of carbon dioxide, UT and RT are used to monitor for loss in thickness. Special emphasis programs to monitor small bore piping, flange face corrosion, blistering, and HIC, SOHIC are recommended as outlined in API RP. UT and RT are used to monitor for loss of thickness. Special emphasis programs to monitor small bore piping, flange face corrosion, blistering HIC, SOHIC are recommended as outlined in API RP 751. Carbon steel operating greater than 150 degrees Fahrenheit. Monitors for thickness loss and may be upgraded to LOE 400. Careful operation of unit to minimize water, O2, sulfur and other contaminants in the feed. Controls on the water content of the circulating acid LOE 400. Solid or clad can be used to eliminate the problems associated with blistering and HIC, HIC, SRHT required to minimize the possibility of SCC. LOC 276 has been used where there have been cracking problems with LOI 400. Upgrade metallurgy utilize chemical inhibitors, blending crude to reduce tan and or increase sulfur content for severe conditions. Type 317L stainless steel and other alloys with higher MO may be required. Environmental cracking carbon steel and alloy 400 can occur in HF R plus hydrogen stress corrosion cracking in HF, blistering in HIC, HOIC damage. Naphthenic acid corrosion NAC, the form of high temperature corrosion that occurs primarily in crude and vacuum units and downstream units that process certain fraction of cuts that contain naphthenic acids. Carbon steel, low alloy steel, 300 series SS, 400 series SS, and nickel based alloys normally occur above 425 degrees Fahrenheit, but has been reported as low as 350 degrees Fahrenheit. Severity as low as 350 degrees Fahrenheit. Severity increases with the temperature up to above 750 degrees Fahrenheit or 400 degrees centigrade. However, naphthenic acid cracking has been observed in hot corrosion hot coker gas oil streams up to 800 degrees Fahrenheit. NAC is a function of the naphthenic acid content, neutralization number, temperature, sulfur content, velocity, and alloy composition. Refer 519. Crude and vacuum heaters, tubes, transfer lines, backbot piping, AGO circuit, HBGO, and sometimes LBGO circuits also reported in LCGO, HCGO streams on delayed coking units processing tan feed. Refer 519. So localized corrosion, pitting corrosion, or flow-induced grooving in high-velocity areas, low-velocity condensing conditions may alloy, including carbon steel, low alloy steel 400 SS, may show uniform loss in thickness and pitting. UTRT monitor tan and sulfur content of the crude charge and side streams to determine the distribution of acids in the various cuts. Corrosion monitoring ER and coupons monitor streams for Fe, nickel content, H2 processing. Upgrade metallurgical chemical inhibitors, blending crude to reduce the tan and increase sulfur content. For severe conditions, types 317 stainless steel or other alloys with higher MO may be required. Sulfidation, note HBGO heavy vacuum gas, LBGO light vacuum gas, HCGO heavy coker gas, HGO atmospheric gas, oil. Phenol carbolic acid corrosion. Corrosion of carbon steel by occur in plants using phenol as solvent to remove aromatic compounds from lubricating oil feedstocks. In order to increasing resistance, carbon steel 304, 316L and alloy C276. Minimal below 250 degrees Fahrenheit. And 304 SS corrode rapidly in phenol service above 450 degrees Fahrenheit. Temperature, water content, alloy chemistry, velocity are the critical factors. Phenol extraction facilities in lube plants. UT and RT to monitor for loss of thickness. ER corrosion probes and corrosion coupons have been used for corrosion monitoring. Proper material selection, control of phenol solvent chemistry, overhead piping circuits should be designed for max velocity. Of 30 fps in recovery section, maintain at least 30 f. 30 degrees Fahrenheit above dew point, 316L or erosion for erosion resistance alloy C276, 316L for erosion resistance. Phosphoric acid corrosion. So phosphoric acid is the most often used as catalyst in the polymerization units. It can cause both pitting corrosion, localized corrosion of carbon steels, depending on water content. In order to increase the resistance of carbon steel, C0, 304L SS, 316L SS, and alloy 20. Typical 304 SS is satisfactory for phosphoric acid concentration of 100% up to about 120 degrees Fahrenheit. Type 316L SS is required from 120 degrees Fahrenheit to 225 degrees Fahrenheit. Acid concentration, temperature, contaminants, solid PA analysis catalysts are not corrosive to carbon steel unless free water is present. When water is present, severe corrosion of carbon steel may occur. Corrosion resistance increase with increase of temperature. Corrosion can penetrate a 1/4 inch thick steel tube in 8 hours. Most corrosion probably occurs during water washing operation of SD chlorides increase EAC, phosphoric acid corrosion. Piping and equipment of polymerization unit where water mixes with catalyst. Low velocity areas where there is little or no circulation such as piping manifolds, the bottom of kettle type boilers, partial penetration wells and exchangers where there is sufficient residence time to permit the settling of acid droplets. General localized thinning. localized thinning of carbon steel UT and RT and loss of thickness plus sample iron in water from first column overhead receiver online corrosion monitoring using ER proofs sand or corrosion coupons in water draw from the first column overhead condenser and the reboiler. Selective upgrading to corrosion resistance material is the only option where water cannot be eliminated. Types 316 LSS and LI20 are defective in concentration up to 85% in boiling temperatures. Type 304 SS is satisfactory for phosphoric acid concentration up to 100% up to about 120 degrees Fahrenheit. Typical 316L SS is required from 120 degrees Fahrenheit to 225 degrees Fahrenheit. Sour water corrosion acidic. Corrosion of steel due to acidic sour water containing H2S at a pH between 4.5 to 7. Carbon dioxide may also be present. Sour water containing significant amount of NH3 chlorides or cyanides may significantly affect pH. Primarily affect carbon steel, stainless steel, copper alloy, and nickel alloys are usually resistance. At a given pressure, the H2S concentration in the sour water decreases as temperature increases. H2S content, pH temperature, velocity, oxygen concentration are all critical factors. Refer 525. Acid sour water corrosion is a concern in overhead systems of FCC and coker gas fractionation plants with the high H2S levels and low NH3 levels. General thinning, localized corrosion, localized only under deposit attack can occur, especially if O2 is present. Corrosion in CO2 containing environment may be accompanied by carbonate SSC 300 SS and susceptible to pitting attack and may experience crevice corrosion and or chloride SCC. UT profile RT process and corrosion monitoring pH provided corrosion coupons. 300 series SS can be used to temperature below about 140 degrees Fahrenheit. Where chloride SCC is not likely. Copper alloys and nickel alloys are generally not susceptible to acids or water corrosion. However, copper alloys are vulnerable to corrosion in environments with NH3. Wet H2S damage and carbonate SCC. Sulfuric acid corrosion. Sulfuric acid promotes general localized corrosion of carbon steel and other alloys carbon steel that affects zones may experience severe corrosion. In order to increase resistance carbon steel 316 SS alloy 20 high silicon cast iron, high nickel cast iron, alloy B3 and alloy C2276. Corrosion varies with concentration of sulfuric acid and temperature. Acid concentration for C is less than 65% temperature alloy content. Velocity of CS if exceeds 2-3 fps. Contamination and presence of oxidizers. Sulfuric acid alkylation units of wastewater treatment plants are affected. DIBOH plus caustic treating sections, BOT for fractionate towers. General But attacks of carbon steel weld has repeatedly. H2 governing may occur in low flow or stagnant areas such as stage tanks or rail cars. H2SSO4 attacks slag left from welding. If chromium and velocity are high, there will be no scale. Corrosion and velocity are high, there will be no scale. Corrosion of steel by dilute acid is usually in the form of overall metal loss and pitting and become more severe with increasing temperature and velocity. UTRT inspection of turbulent zones and hottest area. Corrosion monitoring with coupons and general but at carbon steel weld has repeatedly UT or RT inspection of turbulent zones, hottest area, corrosion monitoring with coupons and ear probes. Corrosion is minimized through material selection and proper operation within design velocities. Alloys such as Li20, Li904L, Li276 resist dilute acid corrosion and form a protective iron sulfate film on the surface. Acidification products streams can be washed with caustic to neutralize the acid known. Okay, we'll stop here.